Okay, so in this video we're going to talk about inscribed angle properties, okay? And an inscribed angle is an angle whose vertex lies on the circle, okay? So the vertex lies on the circle and whose sides contain chords of the circle. So for instance, we have B here is the vertex, AB is a chord, and BC is a chord of the circle, but it helps form our inscribed angle. Okay, so that's different than the central angle. Central angle is at the center, okay? So a central angle has its vertex at the center, and an inscribed angle has it on the actual circle, okay? So that's the difference between the inscribed angle and the central angle. Now the intercepted arc is the arc that lies in the interior of the inscribed angle and the endpoints of the angle, okay? So for instance, when we're looking at the inscribed angle ABC that I just traced out here, ABC, AC is the intercepted arc, okay? That's the intercepted arc that we're talking about when we're referring to angle ABC, okay? Now there's a theorem that says if an angle is inscribed in a circle, then its measure is half the measure of its intercepted arc, or essentially, because we learned from the previous video that an intercepted arc and the central angle are the same, it would also be half the central angle, okay? So half the measure of AC is equal to the angle ABC, okay? So all they're saying there is, if I have my inscribed angle here, AC's measure is going to be double that of angle ABC, or another way to put that is, if I take the measure of AC and I divide that by 2, that's going to give me angle ABC, okay? For instance, if we said that AC here was 50, then angle ABC here would be 25 degrees, okay? And of course, we remember from the last video that the central angle would be the same as the arc, which would be 50. Okay, so the central angle would be the same as this arc. The inscribed angle is going to be half. Okay, now that's also true if we said that half the measure of ADC is equal to the measure of ABC. So let's see, if we're looking at ADC here, our central angle, notice that it's also, the intercepted arc is also half of our central angle, which makes sense because the central angle and the intercepted arc are the same, okay? Now there's a proof to this that says by inserting the radius dB, so we're kind of looking down here now. If we put the radius dB from the center out to the edge of the circle, okay, we split ABC, the angle ABC, into 2 parts, okay? So we're splitting this angle into 2 parts. We have this guy that we're referring to, and then we have this side that we're referring to of this figure, okay? Also, 2 isosceles triangles are formed, okay? So based on what we have here, we have 2 isosceles triangles, okay? So they're saying, notice, this angle and this angle are the same, forming an isosceles triangle because we have, if you recall, the radius is going to be the same, so this would be the same length as this guy, and then vice versa, this would also be the same as this guy because the radius is going to have the same measure, okay? And then also the base angles are the same. So we have 2 isosceles triangles here with the base angles the same and 2 sides the same, okay? And the vertex angles of the 2 isosceles triangles are 180 minus 2x and 180 minus 2, let's call that guy 0, okay? Or O, whatever it happens to be there. So 180 minus 2x and 180 minus 2O. Okay, that sounds like a better guy. So what they're talking about here is these central angles right here. Okay, remember that the angles of a triangle add up to be 180. So if we took x plus the missing side, that would have to add up to be 180. Well, another way to put that is this angle would be 180 minus 2x. And then similarly, if we had O plus this missing side, that would add up to be 180. Or another way to say that is it's 180 minus 2O. Okay, so that would be the measure of that missing angle. We could take 180 minus those 2x's or minus those 2o's to find that missing central angle. Okay, and thus to determine the measure of ADC, we use the measure of ADC. Okay, so let's see if we can kind of go back and highlight this. Maybe we can kind of get rid of our isosceles triangle for a moment. and kind of mark this out. So the measure of ADC, our central angle, plus the measure of ADB, let's see if I can mark that out, ADB, so that guy. Okay, so we're talking about this angle, we're talking about this angle, and then plus the measure of CDB, this guy, so our three central angles there, is equal to 360. Okay, well, why is that? We'll go back to what we know about intercepted arcs. That's one way to think of it. Remember that all the way around the circle here, the arc measures 360 degrees. So if we have three central angles there in the center, ADB, ADC, and CDB, those three central angles have to add to be 360 degrees because their intercepted arcs together have to add to be 360 degrees, okay? So we know that those central angles are going to add up to be 360 degrees. Now, go back to what we said before, though. We said that the measure of ADB here, is 180 minus 2x, and the measure of CDB, this guy right here, is 180 minus 2o. So we can replace those in, and then we'd have the measure of ADC plus the measure of 180 minus 2x plus 180 minus 2o is 360. Okay, well, with a little bit of algebra here, they kind of skip that part. We could actually do that together. 180 plus 180 here, 180 plus 180 here would be 360. So we'd have the measure of angle ADC plus 360 minus 2x minus 2o equals 360. Okay, well, if we subtract 360 from both sides, it would go away. And then if we add 2x and add 2o to the other side, okay, if we move those guys to the other side, we're going to end up with the measure of ADC by itself and 2x plus 2o on the other side, okay? Now, they say, thus that establishes that the measure of ADC is twice the angle ABC, okay? Well, let's just check that, okay? So we're confident that we know that the measure of ADC, kind of go back here, okay? The measure of ADC here is equal to 2 of the x's, notice this x and this x, plus 2 of the o's, that guy and that guy, okay? Well, here's what they're trying to say over here. Notice that the measure of ABC has an x and an o, right? Notice that we just said that ADC is equal to our XXOO. We'll have another X and another O. So that's two X's and O's. So in other words, it's double what ABC is, okay? I have two X's and two O's. So together that'd be twice that angle ABC. So that's how they're establishing that proof of saying that this angle, ADC, is double ABC. Or another way to say that is ABC is half ADC, the central angle. Okay, so that's just the proof behind it. And then it says, if two inscribed angles of a circle intercept the same arc, then those two angles are congruent. Okay, so what they're saying here is if we have two inscribed angles, but these two inscribed angles intercept the same arc, okay? So they have the same endpoints here, AC, they intercept the same arc, then that means those two inscribed angles are the same, okay? So both of those angles would be the same. For instance, if one of them was 20, the other one would be 20 because they both intercept the arc AC, okay? Now the proof behind this is we know that the measure of ABC is half the measure of arc AC, okay? So we just talked about that up here. An inscribed angle is half, the measure is half of its intercepted arc, okay? That's what we talked about in this theorem up here, okay? So whatever ABC is, that's going to be half of what AC is. Well, similarly, whatever ADC is, that's going to be half of this guy too because it has the same arc. So that means if they're both equal to half AC, they must both be equal to each other. That's kind of like our transitive property, right? Take out the middle man. If they both are half of the same intercepted arc, then their measures must be equal to each other, okay? Now let's look at a couple examples here, okay? It says find the requested angle and arc values. Find the measure of, or we're going to find the measure of angle 1 here, okay? Well, it might actually help us to find the measure of arc 2 here first. Notice we have a central angle of 38, and we know that a central angle and its intercepted arc are the same. So the measure of arc 2 here would be 38 degrees. Okay, this would be 38 degrees. Okay, now angle 1 here, whoops, is not a central angle but an inscribed angle. That means it's half of the arc that we're talking about, in this case 38 degrees. So if we take 38 divided by 2 in our calculators, angle 1 here would be 19 degrees. Okay, it's going to be half of what this arc is. Okay, let's try part B here. So on part B, we're given that we have an arc that's 114 degrees. And notice, this is going to help us out, that angle 2 here is actually a central angle. If it's a central angle that intercepts 114, then this must also be 114 degrees. So the measure of angle 2 is 114 degrees. Okay, but angle 1 here, angle 1 is an inscribed angle, and so it's intercepted, when it intercepts the arc 114 degrees, it's going to be half of that. So take 114 divided by 2, and we find that angle 1 here is 57 degrees. Okay, it's going to be half of that. Let's try C. Okay, so on part C, let's just kind of work with what we're given here. We see that this guy is 100. This guy is 134. Whoops, 134. We don't know what the inscribed angle 2 is going to be, but we do know this inscribed angle is 18 degrees. Okay, and that's going to be half of the arc it intercepts with, in this case, arc 1. So if 18 is half of arc 1, how do I find arc 1? Double it, right? Take 18 times 2, and we get 36 degrees. Okay, so this would be 36 degrees. So notice, if we take 36 divided by 2, we get back to our 18. Okay, now that's useful because we know to find the measure of angle 2 here, we know the distance, or not the distance, the arc measure all the way around a circle is what? 360, right? Well, we know 3 pieces of it. We have 100, 36, and 134. Okay, so if we add those pieces together, that's going to tell us how much how much of the arc measure is between those 3 pieces. So take 100 plus 36 plus 134, and that distance, or excuse me, that arc measure right there is 270 degrees. Okay, so whatever remains has to be 360 minus 270. Okay, the piece that remains has to be 360 minus 270. Okay, so take 360 minus 270, and we get that this arc measure, a little bit better, is 90 degrees. Okay, 90 degrees, which makes sense. And if you add it all together, 90 plus 134 plus 36 plus 100 gives us the full 360. Okay, so that's how to work through those. Okay, this next theorem says if one side of an inscribed triangle is a diameter. Okay, so they're saying if one of the sides of our triangle that's inscribed in a circle is the actual diameter of the circle, then the angle opposite, the angle that is opposite on that side here, is a right angle. In other words, it's a right triangle. Okay, so we would have a 90-degree angle. Now, when an angle subtends a diameter, it also subtends an arc of 180 degrees. The inscribed angle is half of its arc, which is 90 degrees. Okay, so this is the proof behind it. We know if we're talking about the diameter EF, then this arc measure of a semicircle is 180 degrees, right? Well, notice our triangle has an inscribed angle that intercepts that arc. Well, what do we know about an inscribed angle? It's half of the intercepted arc. So if this is 180, 180 divided by 2 tells us that this angle has to be 90 degrees, a right angle. Okay, so whenever we're talking about an inscribed triangle and then one of its sides is the diameter, okay, then that angle opposite is going to be 90 degrees. Okay, another theorem here, and then we'll look at that proof and then we can try a couple examples. If a quadrilateral is inscribed in a circle, then the opposite angles are supplementary. In other words, they add to 180. Okay, so if we're talking about a quadrilateral inscribed in a circle, we're saying opposite angles here would add to 180. So D and B and A and C are supposed to be able to add to 180 degrees. Now the proof behind this is they take this quadrilateral down below, and I can kind of point this out. So they say the measure of DAB, that angle measure is half of its intercepted arc, DCB. Okay, that's what we've been talking about. An inscribed angle is half of the measure of the arc that it intercepts. Okay. Then we look at the measure of DCB, and that's also going to be half of its intercepted arc. In this case, the intercepted arc is DB. Okay. Now, putting that together, we know that the measure of DAB, that angle here, plus the measure of the angle DCB, and really you could look at it on the same picture if it's getting a little confusing here. DCB there, those two angles together, is equal to half of the measure of DCB. That's what we said. It's half of the measure of DCB plus the measure of half the measure of DB. So all we're doing is we know that if I add DAB and DCB here, that's equivalent to me saying adding their half of their intercepted arcs. Okay, we're just substituting those values in. Okay, so then again, the measure of DAB plus the measure of DCB, this is called factoring. So if you remember back from Algebra 1, they factored out the 1/2. In other words, it's kind of like the reverse of the distributive property, so they just took 1/2 out. And so now we're saying the measure of the arc DCB and the measure of the arc DB times 1/2 is equal to our two angle measures being added together. Then we have the measure of the arc, the measure of the angle DAB plus the measure of the angle DCB, okay, is equal to 1/2 times 360. Well, why are they saying 360? Well, if we take both arcs, this arc and this arc here, if we look at them both on the same circle, that's all the way around the circle, right? If I just go over here and trace out DAB, notice that goes all the way around a circle. Well, what's the arc measure all the way around a circle? 360 degrees. So if we add both their arcs, if we add both of these arcs, it's 360 degrees. Okay, well, what's half of 360? 180. So what we showed is these opposite angles here, those opposite angles there are supplementary because they add to be 180 degrees. So that's the proof behind it. Okay, so when we're talking about a quadrilateral, opposite angles here are going to be supplementary. Okay, now find the requested angle and arc values. Okay, well, based on what we just said, this is a quadrilateral. 64 and angle 1 here are going to be supplementary, and 58 and angle 2 here are going to be supplementary. Well, let's find angle 1 first. If they're supplementary, that means they add to be 180, right? So work backwards. Take 180 minus 64, and that's going to give us the angle 1 here. So on your calculator, take 180 minus 64, and we find that the measure of angle 1 is 116 degrees. And then similarly, we have 58 plus angle 2 here would be 180. So if we work backwards, 180 minus 58 would give us angle 2. So 180 minus 58, and we get 122 degrees. Okay, so that would be the angles there. On this next example, we also have a quadrilateral, but I also want to point something else out to you that maybe you can't spot right away. Notice we have a diameter, and with that diameter, we're forming a triangle. Okay, so it's not only do we have a quadrilateral here, but we actually have a triangle. And what do we recall about a triangle that's inscribed in a circle whose one of their sides is the diameter? Well, then the opposite that side, opposite the diameter, is a 90-degree angle. Okay, so that's actually going to help us with finding angle 1 here, because if this guy is our diameter, then the angle opposite has to be a 90-degree angle. So angle 1 here is 90 degrees. Okay. Now just kind of clearing that out, finding angle 2 here, they say this guy is 118, and this guy is the opposite angle 2 here. Okay. So we learned up here, just like we talked about, if a quadrilateral is inscribed in a circle, then opposite angles are supplementary. So that means angle 2 plus 118 here has to add up to be 180. So working backwards here, take 180 minus 118, 180 minus 118, and that's going to give us 62 degrees. So angle 2 here is 62 degrees. Okay, so then we have one last problem here. Okay, we have angle 1 and angle 2 to find again. And notice we have a couple of different angles we're looking at. There's a central angle, 102, and then there's also an inscribed angle, angle 1, and then there's another inscribed angle, angle 2 here. So we have a couple of different angles that we're going to use here to help us determine some information. Okay, well, I'm going to start with the central angle. Okay, so the central angle is 102 degrees. What do we know about a central angle and its intercepted arc? They're the same, right? That arc measure and which it intercepts is going to be the same. So this would be 102 degrees from here to here. Okay, now notice angle 1 here is the inscribed angle that intercepts with it. What do we know about an inscribed angle and its intercepted arc? It's half of it, right? So if I take 102 divided by 2, that's going to tell me what angle 1 is, okay? Because it's going to be half of what this guy is. So 102 divided by 2 gives me 51 degrees, okay? So if I know that that's 102 degrees, then I also know we don't even need this 258. We can just work it this way, okay? I also know that every piece here that remains plus the 102 degrees has to add up to be 360, right? All the way around a circle is 360. So if I take 360 minus 102, that's going to tell me this guy right here, okay? So follow along with me here. If we take 360 minus 102, this would be 258 degrees, okay? So that's actually where this guy is showing up again, which makes sense because this angle is going to be the same as its intercepted arc, okay? So this 258 degrees is the same as its intercepted arc. And notice here, if that's the case, this inscribed angle, angle 2, okay, this inscribed angle, angle 2 here, is going to be half of the intercepted arc that we're talking about, this 258 degrees. So I guess we could have used this guy earlier, okay? Is going to be half of our 258 degrees. So take 258 divided by 2, and we find that angle 2 here is 129 degrees, okay? So it's half of that 258, okay? So that's dealing with our inscribed angles and their properties and some proofs to kind of show why things work the way they do. Okay?